In this video, we're going to compute the integral of the inverse sine function on the interval 0 to 1. Now there are at least two ways to do this integral. In this video, we're going to use integration by parts, and in the next video, we're going to use a trig substitution. So to use integration by parts on this, what we realize is that the derivative of the inverse sine function is just a nice algebraic function. We remember that that's 1 over the square root of 1 minus x squared. So we're going to let that part be equal to u, and then the leftover dx, that's going to be dv. So we let u equal the inverse sine of x. And again, you have to remember the derivative of the inverse sine of x to make this work. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. And then the differential du is going to be that times dx. So dv is the other part of the integral, that's just dx. And that means v is equal to x. So then we apply the integration by parts formula, and that starts with u times v, or x inverse sine x. And that's evaluated from 0 to 1. This is a definite integral. And then we say minus the integral of v du. So when we take v, remember that's x, and we multiply by du, we get x over the square root of 1 minus x squared dx. And this is encouraging because it looks like the derivative of the interior function here, so I'm thinking of the interior function as 1 minus x squared, the derivative of that can be constructed up in this numerator. So what I'm doing here is preparing to use the chain rule backwards, or if you like, I've recognized that a simple u substitution will be productive here. Now before I write the next line, we'll go ahead and evaluate across the limits of integration on that uv term, x inverse sine of x. When I sub in the upper limit there, I get 1 times the angle whose sine is 1. Well, the angle whose sine is 1 is pi over 2. And when I sub in the lower limit, x is 0 there, and 0 times anything is 0, so that's gone. As for the leftover integral, I'm going to go ahead and explicitly construct the derivative of the interior function in this thing. And that's a negative 2x. Now to do that, I multiplied the interior by negative 2. And that means I have to multiply outside the integral by negative 1/2. That's going to change this minus sign to a plus and introduce a factor of 1/2 out in front. Again, if you prefer to do an explicit u substitution, you could have just let u equal 1 minus x squared there. But I try to recognize the chain rule backwards directly whenever it's possible. So I'm going to write one more step before I integrate, just to really highlight this chain rule backwards idea. I'm going to write this as negative 2x times 1 minus x squared raised to the negative 1/2. And what I'm saying here is, if I have the derivative of the interior function appearing in the integrand, it makes it very simple to tell what the chain rule is doing, because the chain rule tacks on the derivative of interior functions. That allows us to naively integrate this thing as a power function. So I take the 1 minus x squared and I add 1 to the exponent and divide by the resulting number. So I get a 1 minus x squared to the positive 1/2 divided by 1/2, which is the same as multiplying by 2. When I sub in the upper limit of 1 there, I get a 1 minus 1 in those parentheses, so that one is 0. When I sub in the lower limit, I get a 1 to the 1/2 in there. So remembering that that 1 is going to carry a minus sign because that was the lower limit, and just canceling these 2's while I go, I end up with a minus 1. So we arrive at our final result of pi over 2 minus 1, and we're done. In the next video, we're going to approach this same integral by using a trigonometric substitution instead. I'll put a link to that video at the upper left of the end screen, and I'll see you there.